In this video, we're going to go through section 11.2, which is on vectors. Now, I know this is a topic that probably quite a few of you have seen before, so we're actually going to go pretty quickly through this. We're going to cover everything, though, although, if you haven't seen this before, it might seem like we're moving kind of quickly. So, first of all, what is a vector? Well, a vector can be represented by a directed line segment, right, like an arrow. Okay, so the arrow has the initial point and a terminal point. Okay, so vectors have a direction that they're going in, okay, the direction that the arrow is facing, and also a magnitude, right, or a length of the vector. So as far as notation goes, in these notes, I'm going to use boldface for vectors, so bold type for vectors. When you write handwritten notes, it's kind of hard to use boldface, so sometimes I'll write vectors like this, U, V, W, A, B, with arrows over top. Sometimes I'll do them with hats over top of them. Sometimes I'll just write them as U, V, W, just in normal handwriting, although we want to distinguish them from what are called scalars, right? Scalars are just numbers. So as long as there's no confusion about what's a vector and what's a scalar, you can use whatever notation you like. Okay, so here's the definition. Two vectors U and V are considered to be equal or equivalent if they have the same length and the same direction. Okay, in which case we write U is equal to V. So these two vectors here, they're both pointing in the same direction. Okay, they look to be kind of pointing in the northwest, direction. Okay, but and they have the same length. Okay, but they're at different locations, but we still say that these vectors are equal, okay, or equivalent. Okay, because they have the same length and the same direction. Okay, and that's going to be key, is to recognize that we can move vectors around and you still have the same vector as long as it's pointing in the same direction and it maintains the same length. Okay, so some more notation. If V is a vector from a point A to a point B, so A, let's say, is this point down here, and B is a point up here, we can write V is the vector from A to B, and we write A to B with a little arrow over top of it here. Okay, so this is the vector here from A to B. Right here is what I've written. Okay, so given two vectors, V and W, or U and V, whatever you want to use, how can we add them? Okay, it turns out you can add vectors just like you can add numbers. You can add vectors. And the way that we add them is head to tail. So what do we mean by that? Well, here's our definition of vector addition. Given two vectors, V and W, translate W so that its initial point coincides with the terminal point of V. Okay, then V plus W is the vector beginning at the initial point of V and ending at the terminal point of W. Okay, well, all that wording probably sounds a little confusing until you see a picture. So suppose this is V, suppose this is W. If we want to do V plus W, the way that we can do it is, first of all, we can move these vectors over here. So here's our V, and we can move our W so that its initial point coincides with the terminal point of V, right? So we put the tail of W with the head there of V. Okay, and then the V plus W is going to be the vector that goes from the initial point of V to the terminal point of W. So this is V plus W. Now it turns out that V plus W is the same thing as W plus V, as you can see by this picture here. If we put V here and W there, well, we just as easily could have put W there, and notice that's the same vector as this one, and V here, notice that's the same one as this one, and we get the same terminal point right over here. Okay, so V plus W is, which is this way, is the same thing as W plus V, which would be this way. Okay, so this little parallelogram that we have here is an important picture to kind of keep in your mind. V plus W is the same as W plus V. Okay, now the zero vector, denoted by a boldface 0, is the vector having length 0. Okay, it doesn't have a direction, but it's still considered a vector. So the zero vector is the only vector that doesn't have a direction. Okay, but it's still considered a vector. So notice for any vector V, we have V plus the zero vector is equal to V, and the zero vector plus V is equal to V. Okay, now scalar multiplication. We can multiply vectors by real numbers, which are called scalars. So if you hear the word scalar, it's just talking about a number as opposed to a vector. Okay, and this is called scalar multiplication. So scalar multiplication is not when you're multiplying scalars. Okay, like 3 times 5, okay, is 15. That's not scalar multiplication. Scalar multiplication is when you multiply a scalar times a vector, right? A number times a vector. Okay, so how do we do this? Well, if v is a non-zero vector, okay, and k is a positive number, then kv, okay, so some number times this vector, is a vector that's in the same direction as v, but whose length is k times the length of v. Okay, so here's an example. Suppose this is v. What's 3v? Well, 3v would be a vector in the same direction as v, only 3 times as long. Okay, now notice this is 3 times as long as this. We could think of this as being v plus v plus v. So that's why I've drawn these little extra arrows in here. So 3v, it turns out, is the same thing as v plus v plus v. But it's a vector that's in the same direction as v, only 3 times as long. Okay, now that's if the k is positive. So notice 3 was positive there. What if k is negative? What if you multiply by a negative number? Well, if v is a non-zero vector and k is less than 0, then kv is a vector in the opposite direction as v, and whose length is the absolute value of k times the length of v. So in other words, if here's v, negative 3v would be the vector in the exact opposite direction that's 3 times as long. Okay, it's 3 times as long. So the absolute value of negative 3 is 3, right? So it's 3 times as long, but it's in the exact opposite direction. Okay, now if either k is 0, so if you multiply 0 times a vector, or if the vector itself is 0, so you could do 7 times the 0 vector. Okay, in either of those cases, if either k is 0 or v is 0, kv will be the 0 vector. By the way, with scalar multiplication, notice you're multiplying a scalar times a vector, and you end up with a vector. Okay, your final result is a vector. Okay, so that's why kv would be the 0 vector, not the number 0. Okay, now we use the notation negative v to denote the vector negative 1 times v. So negative v is just a vector that has the same length as v, only in the exact opposite direction. Okay, now vector subtraction is defined as follows. So we can subtract vectors too. V minus w is just the same thing as v plus a negative w. Okay, so geometrically, what does vector subtraction look like? Well, if this is v and this is w, v plus a negative w would be v plus a negative w. So notice I've drawn the negative w is in the exact opposite direction as w, would be this vector. Right, so v plus a negative w, that's this. That's the same thing as v minus w. Okay, and notice, by the way, that v minus v would be 0, so if the 0 vector. So if you take v plus a negative v, you end up right back where you started. Okay, now, so far we haven't talked about vectors as having components. So we've just defined vectors purely in terms of their magnitude and direction, but we can write have vectors that are in coordinate systems. Okay, so we're not defining vectors anymore. We've already defined that, but we're going to talk about vectors within coordinate systems. Now, when we're in 2 space or 2-dimensional space, right, when we have like the xy plane, the ordered pair 5, 2 is a point in 2 space. Okay, it's an ordered pair here. We can also associate 5, 2 with the vector that starts at 0, 0, has initial point 0, 0, and terminal point 5, 2. Okay, in this case, we write 5, 2 with these kind of slanted brackets here to denote that vector. Okay, the 5 and the 2 are called the components of the vector. You call the 5 the x component, the 2 the y component. Okay, or sometimes we'll use I and j. I'll talk about that in a minute here. Okay, but so in other words, the ordered pair 5, 2 is this point. The vector 5, 2 with these brackets is the vector that begins at 0 and ends at 5, 2. And by the way, you can still move that vector around so that you get a different vector in a different location, as long as the vector has the property that it goes to the right 5 and up 2. Okay, then that will be the vector 5, 2. Okay? Now in 3 space, now I'm not going to try to draw this here, but an ordered triple like 6 minus 1, 4 is a point. Okay, you can locate that point in 3-dimensional space. We use the notation 6, -1, 4 with these brackets here to denote the vector that has initial point 0, 0, 0 and terminal point 6, negative 1, 4. And again, you can move that vector around in three-dimensional space, but as long as it points in the same direction and it has that same length, that will still be considered this vector here. Okay, 6, negative 1, 4. Okay, now the 0 vector, of course, is just 0, 0 if you're in 2 space, and it's 0, 0, 0 if you're in 3 space. Okay, so this next thing here is not actually a definition. This is a theorem, okay? If v is the vector v1, v2, and w is the vector w1, w2, okay, if those are vectors in 2 space, then what's v plus w? Well, we've already defined vector addition. Okay, so this is really a theorem here. This is not a definition. V plus w is the vector where the first coordinate is v1 plus w1, and the second coordinate is v2 plus w2. Okay, so you just add the first coordinates, add the second coordinates. And v minus w is defined similarly, v1 minus w1, comma v2 minus w2. Oh, and kv is just kv1 times kv2. So if you want to do the scalar multiplication where you do a scalar times a vector, you can just put that scalar within each of the components. Okay, and you get the exact same thing in 3 space. Okay, if you want to do v plus w, just add up the coordinates. Okay, first coordinates, second coordinates, third coordinates. Same thing with vector subtraction and scalar multiplication. Okay, now let's do an example. Okay, what is 5, 2 plus 1, 3? Okay, well notice 5, 2 is this vector right here. 1, 3 is this vector. Well, when we add these two vectors, remember we can draw this little parallelogram. We could either do 5, 2 plus 1, 3. By the way, this vector here is 1, 3, even though that point and that point, none of those points are 1, 3. The ordered pair 1, 3 is right here. But this vector is the same as this vector, right? Because they have the same direction and the same length. And similarly, this vector over here is the vector 5, 2. Okay, now what is our final vector here? Okay, this what is this vector? The sum of those two vectors? Well, it'll be 6, 5. And notice that's the same thing you get if you just add the coordinates. 5 plus 1 is 6. 2 plus 3 is 5. Okay? And you can see why it works. Why was the first coordinate 6? Well, this first vector, you go over 5 and up 2. The next vector, you're going to go over 1 more. And then up 3. So you went over 5, and then you went over 1 more, so you went over a total of 6. How far did you go up? Well, the first vector you went up 2, the next vector you went up 3 more, so you went up a total of 5. So you see why you're adding them. Okay, so you see why that theorem works. And same thing, what's if v is 2, 1, 7, and w is 4, 0, negative 3, what's 5v minus 2w? Okay, what's 5v minus 2w? Well, there's 5v minus 2w. Now, what's 5 times 2, 1, 7? Well, it's 10, 5, 35. You just multiply 5 by each component. Same thing here. We can multiply 2 times this vector and get 8, 0, 6. And notice we're subtracting here, so we subtract the components. So this vector minus this vector, well, 10 minus 8 is 2, 5 minus 0 is 5, and 35 minus 6 is 29. Okay, so just make sure you know how to do that. It's not hard. Just make sure you know how to do that. Okay, let P1 be the point x1, y1, and P2 be the point x2, y2. So notice I don't have these slanted brackets here. I'm just thinking of these as being ordered pairs. Okay, so we have two ordered pairs in 2 space. How can we find the coordinates of the vector that goes from the first ordered pair to the second ordered pair? Well, the way you do it, and I should have drawn an arrow over top of this, P1 to P2. But anyways, the way that you do this is you do x2 minus x1, comma y2 minus y1. Okay, you subtract the coordinates. So let's see why that's the case, and let's just look at an example. Okay, in 2 space, the vector from P1, which is 1, 3, to P2, which is 4, negative 2, is what? Well, here's the point 1, 3. There's 4, negative 2. What's the vector that goes from 1, 3 to 4, negative 2? Okay, what's this vector? Well, notice, how far are you going over to the right? Well, to go from 1 to 4, you have to go to the right 3. And how far do you go down? Well, to go from 3 down to negative 2, you're going down 5. So you're going to the right 3 and down 5. So this is the vector 3, negative 5. Well, notice we could have gotten that. How did we get the 3? Well, notice we just do 4 minus 1 to give us the 3. And negative 2 minus 3 to give us the negative 5. Now, what would be the vector in the exact opposite direction, from 4, -2 to 1, 3? Well, then we'd have to subtract them the opposite way. So instead of doing 4 minus 1, we'd do 1 minus 4, and we would get -3 in the first component. And instead of doing -2 minus 3, we'd do 3 minus a -2, which would give us a +5 in the second component. So notice that vector that goes from 4, -2 to 1, 3, that would be -3, +5. Right? It's just the negative of the original vector. Okay, well, let's look at a few rules of vector arithmetic. So for vectors u, v, and w, and for scalars k and l, we have these things. Now, we've already talked about the first one. U plus v is the same as v plus u. So that's also called commutativity. Okay, so vector addition is commutative, just like ordinary addition is commutative. Like 3 plus 7 is the same as 7 plus 3. Well, that also works for vectors. This second property is called associativity. Okay, u plus v plus w is the same thing as u plus v plus w. Okay, so vector addition is associative. Okay, we also have u plus 0 is equal to 0 plus u, and by 0 I mean the 0 vector, and both of those are equal to u, so we've already talked about that. U plus -u is just the 0 vector. Now, this one right here, we haven't talked about these last ones. If u is a vector and l is a scalar, this lu, that's a scalar multiplication, and it ends up being a vector. So lu is a vector, and when we do k times that vector, we get another vector. So this left side ends up being a vector. That's the same vector that you would get if you did kl, so multiply the two scalars together, and then do that number times this vector. Okay, so these two vectors are the same. It's always good to think about, what am I talking about, a scalar or a vector? Well, same thing over here. So u plus v, that would be a vector, times k, so k times a vector, that would be a vector. And then again, this is a vector and this is a vector. And it turns out that we have this kind of distributive property, that k times u plus v is the same thing as ku plus kv. And there's also another distributive property here. K plus l times u is the same thing as ku plus lu. Okay, that's a different kind of distributivity, but it still works. And then also 1u, right? So 1 times a vector is just that vector, right? Because it'd be a vector in the same direction as u, and you multiply the length of u by 1. So in other words, you don't change the length. So 1u is just u. Okay, so these are important facts to know, and you should familiarize yourself with them. Okay, now let's talk about the norm of a vector, which is also just called the length of a vector, or the magnitude of the vector. Okay, so the length of a vector v is also called the magnitude or the norm of v. And it's denoted by this. So v, sometimes books will use absolute values, but usually they use this, because absolute value, we try to reserve absolute value for just numbers, like the absolute value of -4 is 4. But when we're talking about the length of a vector, we use these double bars here around it. Okay, so the double bar of v, that represents the length of v. And notice that will be a number, right? Okay, it'll be a non-negative number. So in 2 space, if v is the vector v1, v2, then by the Pythagorean theorem, it's not hard to show that the norm of v is just the square root of v1 squared plus v2 squared. Okay, so notice that will be a non-negative real number. Okay, so that's the length of v. And same thing in 3 space. Now, to see this, you'd have to use the Pythagorean theorem twice to kind of see this. But if v is the vector v1, v2, v3, then the norm of v is the square root of v1 squared plus v2 squared plus v3 squared. Okay, so just a couple quick examples. These are super easy. If v is -2, 3, what's the length of v, or the norm of v? Well, it'll be the square root of -2 squared plus 3 squared. So that ends up being the square root of 13, which is about 3.6056. Okay, so you could actually draw that vector, okay, that goes from 0, 0 to -2, 3, and it would have a length that you would see is between 3 and 4. Okay, now if w is the vector 4, 1, 5, what's the length of w? Well, we can do the same thing. Turns out it's the square root of 42, which is about 6.4807. Okay, now if k is a scalar, then really pretty much just by definition of scalar multiplication, the norm of kv is the absolute value of k times the norm of v. So remember, if k was a positive number, 5 times v, let's say k is 5, 5 times v is the vector that just has the same direction is v, but it's 5 times as long. So if you want to know what's the length of 5v, well, it's just 5 times the length of v. Okay, or if we wanted to know why do we have the absolute value there? Let's suppose k was negative number, so let's say negative 5. So what's the length of negative 5v? Well, the length of negative 5v is just 5 times the length of v. Okay, so remember, negative 5v is a vector that's in the exact opposite direction as v, but it's 5 times as long. Okay, so that's why we have the absolute value there. It's not negative 5 times as long, right? Because you can't have a negative length of a vector. Okay, now a vector that has length 1 is called a unit vector. Okay, now some special unit vectors, these are by no means the only unit vectors, but some special unit vectors are these. So in 2 space, we have a vector that we call I, which is 1, 0. Now the way I usually write I in the notes is I with this little hat over top of it. Okay, and j is the vector 0, 1, and so j, I write it like this. Okay, if you're writing these in your notes. Now in 3 space we have not only I and j, but we also have k. But in this case, I is not just 1, 0, it's 1, 0, 0. And j is 0, 1, 0, and k is 0, 0, 1. Okay, so let's write these vectors in terms of I, j, and k. So it's important for you to be able to switch back and forth between these different notations. So the vector 3, 7 is the same thing as just 3i plus 7j. Okay, because this would really be 3 times 1, 0, which is really just 3, 0, plus 7 times 0, 1, which would just be 0, 7. So what's 3, 0 plus 0, 7? Well, it's 3, 7. Okay. And 4, 5, negative 2 would be 4i plus 5j. You could put plus a minus 2k, or you could just put minus 2k. Now 8, 0 is really 8i plus 0j. Well, if we have a 0j, we don't even really need to write it. Okay, this is really just 8i. Okay, now what's the length of 3i plus 4j? Okay, so what's the length of the vector 3, 4? Well, again, it's just the square root of 3 squared plus 4 squared, which is the square root of 25, which is 5. Okay, so you should be able to switch back and forth between the I, J, K notation and the notation where we have the brackets. Okay, now to normalize a vector, v, is to find a unit vector, which we'll call u, that has the same direction as v. Okay, and remember that a unit vector is just a vector that has length 1. Okay, so we have some vector v, it might have a length of 10, let's say. How could we find a vector that's in the same direction as v, but has a length of 1? Well, it turns out what we do is we just do 1/10 of v. Right, so notice that a unit vector in the direction of v is this. It's 1 over the length of v times v. So again, suppose v had a length of 10, and we wanted to find a unit vector in the direction of v. Well, we just do 1/10 times v, and that new vector would have a length of 1. Okay, and that new vector we would call u. So we could write 1 over the norm of v times v. Another way of writing this is just v over the norm of v. So it almost looks like we're doing a division here, but really this is a scalar multiplication. It's 1 over the norm of v, okay, that's scalar, times the vector v. Okay, so let's normalize a vector here. So find a unit vector in the direction of this vector 2i plus 5j minus k. So in other words, we're going to normalize v. Okay, well notice that v, first of all, has a length of the square root of 30. Okay, we find the length of v, work it out, it's the square root of 30. So v over the length of v, which is the same thing as 1 over the length of v times v. And again, notice it's the scalar multiplication. This thing here is a scalar. This is a vector. So we have 1 over the square root of 30 times this vector. Well, how do we do 1 over the square root of 30 times this vector? Well, we multiply that, each of the components here, by 1 over the square root of 30. So we get 2 over the square root of 30 times I, plus 5 over the square root of 30 times j, minus 1 over the square root of 30 times k. And that's our final answer. And I'm not going to worry about rationalizing the denominator here. But notice this is what you get. Now you could write it in this notation, this bracket notation as well. 2 over the square root of 30, comma 5 over the square root of 30, comma negative 1 over the square root of 30. Okay, so this vector has the same direction as the original one, but it's not as long. Okay, the square root of 30 is what, like 5 point something? It's somewhere between 5 and 6. So these two vectors, this vector here, or this vector, and this vector, they're the same direction, only this one is like 5 or 6 times as long. Okay, it's the square root of 30 times as long as this one. Okay, but they're facing the same direction. Okay, so notice that a vector v is obviously equal to the norm of v over the norm of v, right, which is just 1 times v. Okay, but notice that v over the norm of v, we could write that as u. So v over the norm of v is just a unit vector in the direction of v, and we'll use that letter u to denote that. So we can always write a vector v as the length of v times a unit vector that's in the direction of v. Okay. All right, so that's important to know. Now, also, we're not going to get into the physics of vectors so much, but a lot of times vectors, probably the first time you've seen vectors maybe is had to do with something in physics, so maybe having to do with force. So let me at least just mention this, and this is the last thing we'll talk about here in this video. The effect that a force has on an object depends on both the magnitude and the direction of the force. Okay, and the point at which it is applied. So forces can be regarded as vectors. Okay, so if you're pushing up against something, so you're pushing a car, let's say up a hill, okay, you're applying a force, okay, with a certain magnitude, right, and in a certain direction. Okay, so a vector can be, or a force can be thought of as a vector. If two forces, F1 and F2, are applied at the same point on an object, then the two forces have the same net effect as the single force, F1 plus F2, applied at the point. So F1 plus F2 is called the resultant of F1 and F2. Okay, and we say that F1 and F2 are concurrent to indicate they are applied at the same point. So a lot of applications of vectors. We're talking about them from a purely mathematical standpoint in this video, but there are lots and lots of applications of vectors, especially in things like engineering and physics.